section 16.7 is on page 1032, talks about Stokes Theorem. And this is not going to be something new, something you've seen before. I'm going to correlate that to you. Let S be a piecewise smooth oriented surface having a piecewise smooth boundary, which means you could boundary curve, which means you could differentiate it. Let F be ijk vector field having continuous first partial derivatives on an open region containing S, all of that awesome stuff. The circulation of F around C in the direction counterclockwise with respect to the surface unit normal equals to the gradient crossed with F. So, if you recall, we did this already using Green's theorem, right? And we called this the curl of F. Dot it with N. I'll talk about N in a minute. And this is kind of like was our ds, so to speak, if you remember. So this was the square root of f sub x squared plus f sub y squared plus 1 dA. Provided you look at this from the z direction, you could alter that accordingly. Or this was, if you remember, magnitude of r sub u crossed with r sub v dA. Luckily, it doesn't change here. And I'm talking about Green's theorem. Green's theorem, we did exactly the same work. We took the integral, closed integral along around C of f dot dr, and we got it to be this, except we were doing it on 2 dimensions. F was actually only consistent of m and n. Now we're doing that on 3 dimensions. So Stokes theorem is Green's theorem to 2 dimension. Green's theorem is for 3 dimensions, and everything matches. The work is the same, except we really didn't have such a hard time finding n in 2 dimension. In 3 dimension, you really gotta think about that a bit more. And that's about it. That's what this is. This is a straightforward section, really. And I'm gonna do some problems. Before I do examples, I just wanted to write those out. If I take the curl of f and the area of the length, that would be the double integral over S, the curl of f, and n, if I'm given a vector, it's going to be r sub u crossed with r sub v, that's perpendicular, divided by, that's the normal vector to both, divided by its length. That makes it a unit vector, or unit normal, I should say. And the s in this case, what are we gonna call it? I keep forgetting what that is. The rho is gonna be r sub u crossed with r sub v dA. And you notice that those cancel out. Or you would say this is the double integral over region D of the gradient crossed with f, the same thing that doesn't change, times the square root of f sub x squared plus f sub y squared plus 1 squared dA, right? Given z equal f of x, y, and here given r of u and v. And that's pretty much the difference between those, right? Because here the unit normal, in case I didn't write it down, I should have. You know what, an extra step is not going to hurt. Okay, third time will be a charm. So here, if I want the normal vector, this was the normal vector. Here the normal vector would be the gradient of f divided by the magnitude of the gradient of f. And z equal f of x, right? And it turns out that those cancel out. And we'll mention what that is. And I'll point those out as I do examples. That's not a problem. Let me look at the first example. I'm looking at page 1043, problem number 8, directions in 7 through 12. Use the surface integral in Stokes Theorem to calculate the circulation. Alright, we know they're talking about f dot dr, and according to Stokes Theorem, which is provided on the final exam, it's going to be the curl of f dot n d rho. Well, let's write what everything is. Let's figure out what each of those would be. That's going to be the double integral. And let's see, if I take the curl of f, that is del. So when we did, oh, and I forgot to mention, yeah, when we were talking about this. So here, this is, I don't know if I mentioned, yeah, I did. This is Green's theorem, and this is Stokes' theorem. The difference is, this right here is the floor right there. So this was done on 2 dimensions only, figuring out on the surface, on the ground. This is figuring out on this 3-dimensional oriented surface. What's happening? There's the normal. Right? So, ijk, the partial with respect to x, the partial with respect to y, and the partial with respect to z. So this is just like Green's theorem, except it has the k component. And if I take my vector field, which is 2y, 3x minus z, I'm going to get in the I direction, it looks like a 0, the j, negative 0, a 0 as well, and in the k, I'm going to get a 3 minus a 2, which is 1. So I got 0, 0, 1. Oh, what a coincidence. So curl of f is 0, 0, 1. This part I have to get, it says counterclockwise as viewed from above. If I'm looking from the top down, doesn't that mean I have 2 options? Either I'm going to dot that with 0, 0, 1 or 0, 0, negative 1. Am I going to hold the direction in a very high point as far as grading? And this right here, if I want to work out what this is, well, isn't that a 1 as well in this case, because that has... Alright, so this is pretty much the circulation. Now, what's the region? I have this vector field running. The circle x squared plus y squared equal 9 in the xy plane, counterclockwise when viewed from above. Alright, well, if this is going to get me a 1 dA, and I know we're talking about the area of a circle, well, do I need to do any work? Can't I say that is actually pi times 3 squared, which is 9 pi? Right? Or I could describe that using polar coordinates, x equal cosine, y equals sine, 3 and 3, and so on and so forth. Looking at number 10. Well, the same deal. If I want the closed integral of per c of f dot dr, that's going to be the double integral over, in this case, the region D of what? Curl of f n factorial. Yeah, right. D rho. Alright, well, let's figure out what those are. Let's get this out of the way. If I want to take the curl of f, partial with respect to x, partial with respect to y, partial with respect to z, of y squared plus z squared, x squared plus z squared, and x squared plus y squared. And that would be the partial with respect to y, that is 2y minus the partial with respect to z, 2z. And if I look at the j component, that is the partial with respect to x, that is 2x minus the partial, that's 2z as well. And the k component, partial with respect to x minus partial with respect to y. Alright, so this is what I'm getting. So this is pretty much 2y minus 2z, negative 2x plus 2z, or 2z minus 2x, and 2x minus 2y. There it is. If I want to know what the normal is, this is the plane. How do you find the normal to the plane? Well, the gradient of f divided by the magnitude of the gradient. The gradient is actually 1, 1, 1. And the length of that, isn't that radical 3? There it is. And if I get to the actual length, wouldn't that be f sub x squared plus f sub y squared plus 1 squared? And you're going to notice, isn't it right there? Isn't that the square root? F sub x squared is 1 squared plus 1 squared plus 1 squared. So like I said, they cancel out. You could skip that if you want. Those two are gone. And I'm looking at the double integral of, let's see, 2y minus 2z minus 2x plus 2z plus 2x minus 2y dA. And how am I going to describe a? Well, that depends on which way am I going to look at that. So, oh, those cancel out. It's a 0. Just to elaborate, if this wasn't 0, you were going to look at this from above, right? And you know how this works. 1, 1, 1. So if you were looking at that from above, you would really be looking at x plus y equal 1, and you could do dx, dy, dy, dx. It makes no difference. Number 12 is next. I'm given a vector field, and the intersection of this, well, I don't need the graph, but here it is. This is f4, and I have the sphere, and x plus y equal 2. So, when you look from above, the only thing you're going to see is really this circle. But you need to compensate for the three-dimensional portion, and you're going to say, well, the integral of f dot dr along C is going to equal the double integral over the region of, and let's see, if I take the curl of f, curl of f turns out to be 0, 0, negative 3 x squared y squared. Partial with respect to x, partial with respect to y, partial with respect to z, and you can do it right here. That's a 0. Let's say that's a 0 with respect to z. The only one would be left. That would be 0, 0, negative 3. And you could do that as a practice. N, I need n for this three-dimensional figure, and what n is would be the gradient of f divided by magnitude. Well, the gradient of f is going to be the square root. The gradient of f is going to be 2x, 2y, 2z divided by the square root of 4x squared plus 4y squared plus 4z squared, dotted with the well, which is the square root, and it's right there, they cancel out, just like we said. And those undo each other, and you are left with simply negative 3x squared y squared dA, in which A is this area, And you could do that appropriately by converting to RD theta is suppose 0 to 2 pi, 0 to 2, -3, r squared cosine squared theta, and r squared sine squared theta. And there it is. And there's the homework for this section.